So this will be the third and final lecture over alkynes. So third lecture out of chapter 9. So in this lecture, we'll look at the reactions that alkynes undergo. So the last lecture, we looked at how to make alkynes. And so now once you have an alkyne, what kind of reactions can you do with them? And these reactions are pretty easy if you know the reactions of alkene really well, alkenes from chapter 8. So if you know those reactions really well, this is easy because alkynes react similar to alkenes. It's just that you have two pi bonds, so you typically just do the same reaction twice that you would do to an alkyne, what you would do to an alkene. So what does H2 and palladium do to an alkene? It adds hydrogen and hydrogen across the double bond. Well, it does the same thing here too. So we go add hydrogen and hydrogen across the triple bond. So you would add a hydrogen and a hydrogen to both of those carbons. That would give an alkene, but alkenes react with H2 and palladium. So as soon as you make this, it's going to react again. And you're going to make the alkane. So it's going to reduce all the way down to the alkane. So it's very difficult to stop here. So if it's just H2 and palladium that you're reacting with, it's almost impossible to stop at the alkene. As soon as the alkene is made, then it's going to react again to make the alkane. So it would be nice to be able to stop it at the alkene because as we saw in the last chapter, there are a lot of reactions that alkenes undergo. So this would be one thing that chemists do, is they just go into the lab and they try to discover new reactions. So how can you take an alkyne and stop it at the alkene? And so one way to do that is this recipe, to take an alkyne with H2 and what's known as Lindlar's catalyst. So Lindlar's catalyst is this. It's palladium, calcium carbonate, and quinoline. So this is what quinoline looks like. Or the more modern recipe, that's the improved version, is palladium, barium sulfate, and quinoline. So basically what this does is it poisons. So it poisons the catalyst. And that makes it less reactive. So this will allow you to reduce the alkyne to the alkene, and it will stop there. And so what else do you know about the addition of H2 on a palladium surface? Is that it's a syn addition. So the hydrogens add to the same side. So in this particular example, you couldn't see that. But it's gonna, well, we'll just put these in red. Not that you can distinguish between hydrogens. So it would add two hydrogens to the same side. So you get a syn addition and it stops there at the alkene. But of course, since this carbon has two hydrogens, you couldn't tell which hydrogens were added syn to each other. But in a reaction like this, you could tell. So if you took that alkyne with H2 and Lindlar's catalyst, so you may just see me on a test write H2 and Lindlar's catalyst, or you may see me on a test write H2, palladium, calcium carbonate, and quinoline, or H2, palladium, barium sulfate, and quinoline, and you would just have to recognize that's Lindlar's catalyst. So that's going to add H and H across the double bond, and it's going to be cis to each other, or syn to each other. So you would make the cis alkene. And so you'd want to make sure you recognize that because the stereochemistry is part of the problem. So this is an important reaction because it's not easy to make cis alkenes, right? Usually if you do an E1 or E2 elimination, you would typically make the trans alkene because it's thermodynamically more stable. But in this particular reaction, it only makes the cis alkene. Okay, so what if you wanted to make the trans alkene? Well, there's a recipe for that. So what you do is take an alkyne and you take a group 1 metal. So it could be sodium, it could be potassium, for example, lithium, and then your solvent is typically ammonia. And so if you do that, so all it does is add H and H across the triple bond, but it does so to make the trans product. Okay, so how does that happen? So this is the basic mechanism. So group 1 metals have 1 valence electron, right? And they have a very low ionization energy, so they really want to get rid of that electron. So it can give the electron away to the pi system. So we're going to give this electron from sodium to that carbon, so we're going to split the triple bond. So this is going to become a lone pair on that carbon, and the other electron is going to stay behind on that carbon. So one carbon's become a radical and the other carbon becomes an anion. So now you have a carbon with a negative charge on it. That's a very strong base. So what it does is that carbon lone pair picks up a hydrogen from the solvent, ammonia, and you make NH2 minus as a side product. So that would give you this free radical, where now you've added 1 hydrogen to the alkyne. So this radical can exist as different stereoisomers, the cis or trans version, and of course the trans is going to be more stable because the 2 R groups are further apart, and this would be the cis version. So once you make this radical, it can convert between the cis and trans versions, and the trans is more stable, so you're going to have more of that in solution. And so now this reaction just repeats itself. So sodium is going to give up another electron to make another carbanion, and then that carbanion is going to take another hydrogen off of another molecule of ammonia, and then you have the cis alkene and another NH2 minus side product. So basically what happened in this reaction is 2 electrons transferred from sodium, from the metal, lithium, sodium, potassium, and 2 hydrogens transferred from ammonia. So you basically just added 2 hydrogens and 2 electrons across the triple bond. Okay, so just to summarize that, so if you took this alkyne with H2 and this is Lindlar's catalyst, then this is going to make the cis alkene. And if you did a metal and ammonia instead, then that's going to make the trans alkene. But in both cases, you just added hydrogen and hydrogen across the triple bond. But you would need to clearly illustrate the stereochemistry, know that it's cis or trans. Okay, so in chapter 8, we looked at the addition of HX, HCl and HBr across a double bond. So if you remember, what this does is to add H and chlorine, or H and bromine across the double bond. Is it Markovnikov or anti-Markovnikov? It's Markovnikov. So basically you're just going to do that twice. You have 2 pi bonds, you're going to add H and bromine across the triple bond twice. So this carbon has no hydrogens. This carbon has 1 hydrogen. So Markovnikov's rule says that hydrogen is going to go here and the bromine is going to go there. So you're going to add hydrogen to this carbon and bromine to that carbon, and then it's going to do the same thing again. So technically you need 2 equivalents of HBr, so you might just see excess wrote on the arrow, or you might see 2 equivalents of HBr. So it'd be very difficult to stop here. Alright, as soon as you make the alkene, it reacts again, and you just add another HBr across the double bond, and now you have the geminal dihalide. As we talked about that in the last lecture, how we were trying to synthesize an alkyne, but you couldn't synthesize it, and having the so we, in order to make the geminal dihalide, right? This is geminal. You needed the alkyne, so it didn't make sense to synthesize an alkyne just to make the geminal dihalide and then go right back to the alkyne. So that's the only way that we'll look at in this semester how to make geminal dihalides is from the alkyne with excess HBr or excess HCl. Okay, so if you remember this recipe from alkenes, what does this do? It adds H and bromine across a double bond, but it's anti-Markovnikov. So this has 1 H and this has 0 H. No, I did this. Sorry, I just did this previous problem totally backwards. So this is totally wrong, right? Because this is Markovnikov. So we should be adding the hydrogen here to the carbon with the most number of hydrogens and the bromine here, right? So we should have added CH3, bromine here. And then we should have did this again. And that would be your final product. Where we add HBr twice. H goes to the carbon with the most number of hydrogens since it's Markovnikov. This, however, is anti-Markovnikov. So now we would want to put the hydrogen on the carbon with the least number of hydrogen. So hydrogen's going to go there and bromine's going to go there. We're just going to do it 2 times. Doing it backwards again. So H goes there, bromine goes there, and then you do that again. So now 2 hydrogens go there, and 2 bromines go on the first carbon, the one with the most number of hydrogens, and that would be your major organic product. And so again, in all of these reactions, it's difficult to stop it at the alkene, so you should just recognize you're just going to do this reaction twice, and as soon as you make the alkene, it's going to react again. Okay, so in reactions of alkenes, we looked at the hydration. So if you did H2O and H2SO4, that adds H and OH across a double bond, and it does so Markovnikov. And that's going to be the same thing here. So if you added H, so H would go here, and OH would go here, right? So that would be the Markovnikov addition of H and OH, but this reaction does not stop there. This is what's known as an enol functional group, where you have an alkene and an alcohol attached to it. And so these undergo a process called tautomerization. So enols in general are not very stable. Sorry, there's no hydrogen on this carbon. All kinds of mistakes here, right? That carbon would have 5 bonds if there was a hydrogen there. There's no hydrogen there. We just add H and OH, and then that's your enol. Okay, so tautomerization, the enol form is always in equilibrium with the ketone form. So this is not the mechanism how this happens, but it's just a way to think about it. So take the hydrogen and move it down, and take the double bond and move it up, and then that would be the ketone form of the molecule. So that would be your major organic product. So in terms of the mechanism, how does this work? So the mercury sulfate is in there. It's just a catalyst. So that's a mercury 2+ cation. So that adds to the alkyne. Right, and then water attacks. And then let's lose a proton from the H2O. And the 2 electrons become a lone pair. Okay, and then what happens? So we add a hydrogen to the molecule now. Right, and then you lose the mercury. So the mercury Hg2 plus comes back off of the molecule. So take those electrons in the carbon-mercury bond, make your carbon-carbon double bond, and now you have the enol. So Hg came back off, so you used Hg2 plus to get the reaction going. You get it back at the end, so it's not used up, so that makes it a catalyst. So when that comes off, you make the carbon-carbon double bond, so that's the enol, and then the enol tautomerizes to the ketone. Okay, so if that's a symmetrical alkyne, then you only get one possible product, but if it's a non-symmetrical alkyne, so as in this case, well, now you can't apply Markovnikov's rule, right? Because both carbons have the same number of hydrogens, none. So that means you could add the H here and the OH here. Right, or you could have added it opposite. You could have added the OH here and the H there. So that would be 2 possible enols, and then they will tautomerize to the ketone. Okay, so again, just flip the double bond up to make a C double bond O and move the hydrogen down. And you would get CH3, CH2, C double bond O, CH2, CH3. Or from the other one, if it tautomerizes, well, it does tautomerize. Not if, it will. Then that would be your ketone. So if non-symmetrical alkyne, then you're going to get 2 possible ketone products. Okay, so that's the Markovnikov addition of H and OH across the triple bond. As we saw in alkenes, it's also possible to do anti-Markovnikov addition of H and OH, and that was through the hydroboration oxidation reaction, and so this is analogous to it. So this SIA is just an abbreviation for this, for that carbon chain. So there's just 2 of those attached to boron. That makes the boron very sterically crowded, and only one BH. So only one of these alkynes is going to add to the boron. So that's the purpose of this sterically bulky SIA group, is just to make sure only one alkyne adds. So basically you add boron and anti-Markovnikov, so CH3, so that means the hydrogen is going to go to that carbon, right? The one with the least number of hydrogens. So H goes there, and the boron would go there. And then when you do the H2O to OH step, so that's going to replace the boron with OH. So now you have an enol, and that's going to tautomerize to the aldehyde form in this case. So again, this is not the mechanism. It's just a way for you to think about predicting the product. So we're going to take the double bond and move the double bond there, and move the hydrogen there, and then that's your product. Right? So again, you make a C double bond O. So basically the way to think about predicting these products is going from there to there. You're just going to add H and double bond O. So you're going to add water across the triple bond. One carbon is going to get two hydrogens, the other is going to get the double bond. And so same is true here. It's just that this is Markovnikov. So if you did this recipe, they're going to add H and double bond O across the triple bond, and then that's going to lead to that ketone as the product. Okay, so just to re-emphasize that, so if we took this alkyne with the Markovnikov versus the anti-Markovnikov version of adding water, so we would get that for the top reaction. So we added H and H here, and we added C double bond O here. Or if we do the bottom reaction, then we're going to add H and H here and double bond O here. And you would get the aldehyde instead. Okay, so two more reactions of alkynes. So if we take an alkyne with CO2 or Br2, if you remember, what does this do to an alkene? It just adds X and X across the double bond, anti to each other. So it's just going to do it twice for the alkyne. So if we did bromine and bromine, would add bromine and bromine across the triple bond, anti to each other, but it doesn't stop there. And then we do it again. So now we add bromine and bromine across the double bond, and so you end up adding 4 bromines to the molecule. Or if this was chlorine, you would add 4 chlorines to the molecule. So that would be your major organic product. And then lastly, we looked at the O's analysis of alkenes. And if you remember what happens to alkenes, you cleave the double bond, does the same thing to triple bond. So we're going to cleave the triple bond. So let's cleave the triple bond, but it's a little bit different for alkenes, for alkynes, and the second step is just water. And so what's going to happen is both of the alkyne carbons will be oxidized to carboxylic acids. So just split the triple bond and then make both carbons of the triple bond into carboxylic acids, and that's your product. All right, so if we did this reaction, with ozone and water, then we're going to split the triple bond. That carbon will become carboxylic acid, and the other carbon will become carboxylic acid. And so we won't look at a mechanism there, you just have to learn the reaction, be able to predict the product. Okay, so that's it for chapter 9. So that's all the reactions of alkynes that you'll have to know.